Welcome to the evolving world of iron making, where every normal meter cube of gas injected is more than fuel. It's a step forward, redefining blast furnace efficiency. Today we explore how a strategic injection of gases like coke oven gas and natural gas is transforming the way steel is made. So, primarily, our comparison lies on two gases, one is coke oven and other is natural gas injection. Now, question arises that why CRR matter? So, let's say we inject 18,000 normal meter cube of COG per hour with a CRR of 0.75, that's 13.5 tons of coke saved every hour, which is a huge amount. Over a 300-day run, this translates to nearly 1 lakh tons of coke saved annually. So annually the figure is huge. That's not just operational efficiency, it's strategic decarbonization at scale. Now, coming to the understanding of CRR, which is very important, and unless until we have a right understanding of CRR, our methodology, our saving uh, towards the strategy selection will be not right. So, understanding of CRR is important. Cook replacement ratio is influenced by several factors, and these factors are enumerated in this slide. The first one is the gas composition. So, once composition is changed, the calorific values change and the coke replacement ratio will also change. Hence, gas composition is important factor. Then the injection rate, at what sort of injection rate we are maintaining, is that injection rate is optimum to have a fine burnout ratio or not, that is also important. So, and for burnout, you we have a everything in place or not. Everything in place means right oxygen enrichment, uh, correct flame, right blowing. So all these are in place or not. So unless until all favor together, the burnout will be not optimum. The interior design is also important, as you must be knowing, as gases combust, it produces a lot of volume, and there is increase in pressure. So there are many to a design which are towards end they are divergent to accommodate this sort of gases. So two a design is also one of the important aspect to accommodate that sort of injection and giving a value for right value for CRR. And the furnace geometry ultimate is this is important. So we can summarize each replacement CRR factors like gas composition, injection rate, tuer design, and furnace geometry. So together they determine how effectively injected gases can replace metallurgical coke in the reduction zone. Now coming to the next slide, which is about the chemistry of COG composition, which we have just discussed in earlier slide. COG is not a waste; it is an untapped reductant. And a reductant means a hues, because today's we are talking about a hydrogen injection, and this cocoa gas has already around 60% or more hydrogen in it. So it's a sort of a good, it can be a good experimental hydrogenaceous based fuel for blast furnace to see that what sort of anatomy, what sort of configurational changes in the Bosch belly region, the temperature profile, the utilization, the retention time of hydrogen, and so many things. So it's a full of a research scope. This gas is. So with nearly 60% hydrogen and 25% methane, its reducing power is immense. Hydrogen and carbon monoxide participate in the reduction of iron oxide significantly, and this is significantly easing the burden on coke. So we can have a this very favorable chemistry of coke oven gas to evaluate the effect of it in the furnace, and which can be showcased for future learning when hydrogen becomes cheaper, and we can got a plenty of hydrogen at that time. These study outcomes will helpful. Now coming to few case study which also gives us a lot of benefit in understanding this sort of a injection and CRR value. So as you can see that this is from the Nippon Steel. At Nippon Steel, injecting 15,000 normal meter cube per hour of coke oven gas yielded a CRR of zero point 0.7. That's 700 kg of coke saved per 1000 cubic meter. An impressive testament to the value of hydrogen rich gases in established operation. Now coming to the another case study which is about ArcelorMittal Europe, and in Europe ArcelorMittal achieved a CRR of 0.65 through optimized to design and oxygen enrichment. It's a clear example of how design and control amplify the impact of gas chemistry. Now coming to another case study of Bosch Steel. In China, Bosch Steel harnessed high CH4 content in COG to reach a CRR of 0.75. Methane, when partially oxidized, act not only as a fuel but also a secondary reductant, turning combustion into chemical leverage. So let us discuss the science, the CRR formula. The empirical formula behind the CRR is straightforward: zero point 0.6 times the hydrogen content, 0.4 for CO, and 0.3 for CH4. Input the gas composition and you unlock its coke saving potential with mathematical precision. So it's a nice formula which looks simple, and immediately it can give us a result. Now coming to the this slide which is having a natural gas versus COG comparison, a comparative view. While COG outpaces natural gas with a CRR of zero point 0.7 versus 0.32, that is, both gases contribute uniquely. COG's hydrogen strength and natural gas methane content can be deployed strategically depending on cost, availability, and furnace configuration. So this is a nice time for a operator to decide that based on market condition what sort of combination he has to choose to optimize the hot metal cost. So finally coming to the recommendation and path forward, the path ahead is clear. pilot trials at BF uh, integrate oxygen enrichment and collaborate with technology providers with every normal meter cube validated and optimize. We forge a learner, a smarter, more sustainable way to make steel. Thank you.